Okay. Hey, happy Tuesday, everybody. Say hi to Professor Gumbel. I'm going to go ahead and record this and upload it now. I know it's a little early, so instead of meeting everyone at 2:30, I'm just going to go ahead and record this and post it now because I got to run some errands this afternoon. So I'm going to go through kind of the second half of feature detection and FLAN. Um, just one announcement, well, a couple announcements. So I'm going to post project 3 today. It's going to be due on the 17th. Um, and then the other thing is, so this is the rest of FLAN. The last thing I had planned on covering this semester is YOLO, which is kind of the next step up from FLAN. And we're going to talk about that Thursday and probably a little Tuesday. And after that, the last couple of weeks are pretty much wild card. So feel free to kind of drop any topics in the Discord you're particularly interested in, or any CV applications you might want to learn more about. And if people are interested in one thing or another, we can kind of do a class or two on it, just to have some a little bit of free time here at the end, because we got through everything a little bit faster than I thought. So anyway, I'll get going here. Let me share my screen. Zoom. All right. So this is a follow-on to Thursday's lecture. So it's kind of feature extraction part 2. Last time we talked about this, we've talked about this a whole bunch. We've got our feature matching, where we want to find all our key points with some sort of algorithm like SIFT or SURF. And then we want to compare each feature vector for our key points against the feature vector of our sort of source image of the object we're trying to find. And so we talked about this, right? We've got our low level with our edge detectors and working with color spaces. We've got mid level with Q transforms of parameter spaces. And then we've got our high level features, which is where we are now with SIFT and SURF and FLAN. And next time we'll talk about YOLO. But the idea being, we know how to find all the key points. We know how to get all of the key points feature vectors. Now we're looking at different ways of comparing a key point to our source image to figure out where all in the image is the object we want. Feature space, we've talked about this a whole bunch. Kind of the type of features that go into a feature space. It's just a big old multi-dimensional space. Every entry is a characteristic that has something to do with the object we're looking for. And the types we've talked about for our feature matching, where we've talked about brute force a lot. We're in the middle of talking about FLAN and KNN. And then we'll wrap this up with YOLO this week and next. So we talked about some anomaly detection. We talked about the idea that we are working with contextual anomaly detection, which is the sense that there's some sort of background to the image, there's some sort of context that everything sort of falls into, that's got kind of its own descriptors and, so on and so on. And then we want to find the things that are different from the broader context of the background image. We want to find those key points. And we find those using, this concept of anomaly detection, where we want to know, which thing is different from all of the other things and is different, in the way what I want is different through the features. Let's just kind of going over that. We're talking about, we want to know about contextual anomalies. And you know what? These are the wrong slides. So hang on 1 second. Pause. All right. Okay. I found it. Back to sharing my screen. All right. Yeah. So this is what I'm saying. We're on FLAN. So when we're talking about flan, I think I've got my shit together. Yes. Okay. So blah blah blah. Contextual anomalies are types of feature matching. So we're talking about flan right now. What we have done till now, until Thursday, is we've been talking about finding features and we've been talking about extracting those features through their feature vectors. So feature matching or object detection and classification is what we're going to call it with YOLO, but matching features, um, that starts after we have found them. So the things we're going to do to match features happen after we've already done a key point detection algorithm like SIFT or SURF or ORB, which is our OpenCV version of SURF. And so it's kind of that next step up the ladder where I have extracted my features via key points. Right now I'm matching those features to the feature vector of the object I want. So this is, like I said, another step sort of up the CV ladder where we've already found our features. Now we want to match them to the feature I care about. And again, we talked about this. And so FLAN is the fast library for approximate nearest neighbors. And what it is it's a search algorithm that is built for high dimensional spaces. So remember, we talked about the feature space. A feature vector is usually going to have, 500 or 1024, a huge number of dimensions, right? It's not just an XYZ or an XYZ in a color. It's a full feature space that, has for each feature vector hundreds or possibly thousands of dimensions within each vector. So what we do do is a nearest neighbor search. We're going to approximate it because as we've talked about over the course of the semester and a lot of things we've done, we can do this with brute force where we just compare every dimension of every feature vector to every dimension of our source feature vector and find, our vectors that are close enough. So it's an approximate search. It's kind of the same way SIFT was looking at everything. SURF was a speeded up approximate way of looking at things. FLAN is another way of using an approximate search to try and find things without going through brute force. And so the way FLAN works, the way this sort of nearest neighbors works is, like I said, the first thing we're going to do is find our features with our feature detection or extraction algorithm, SIFT, SURF, whatever. Then we're going to go in and use FLAN to find the features, to match the features. And so it does this a couple ways that I'm going to talk about, but in general, it uses either a tree structure, like a forest structure and a tree search, or it uses hashing. And the other thing about FLAN that, we start from SIFT and SURF, and then we do a feature match with our nearest neighbor search methods like trees or hashing. What we do afterward is run a RANSAC algorithm, which is a random sample consensus, which I'll talk about in a minute. And then it gives us back our features, and then it stitches our image back together. So this is our nearest neighbor search. So this is the NN at the end of FLAN. And like I said, there are a couple ways it does this. These are the four I'm going to kind of cover for our CV class, which is, our brute force, which, like I said, is the best for everything. And then also that's the best for nothing because it's so slow. for really complicated images. So sort of the base version of Flame uses a KD tree, which is essentially just a binary tree search. So it chooses some dimension within the feature vector and creates a split out of that, or a leaf in a tree. And then it just runs through several different dimensions in the feature space to sort of do a binary, yes, it matches, no, it doesn't match, based off of that feature, and then works its way down the tree. It is best for low dimensional data, because if you think about how you're splitting binary trees based off of dimensions within the feature vector, if your feature vector is, say, 1,000 dimensional, then that is a lot of binary trees to split, essentially. But because it is a binary search and it is going through just sort of single entries in the feature vector iteratively, it requires the least amount of tuning. If you just sort of do it this way, you can give OpenCV very simple parameters and just kind of let it do its thing. But for it to work, it does kind of need low dimensional data. So it would work much better on the output of a surf key point extraction, because that's a 500 dimension feature vector. Then it would work on a SIFT feature extraction, which is a little over 1,000 dimensions. Next, nearest neighbor search option is hierarchical k-means. And what that means is instead of creating trees for dimensions in the feature vector, it chooses features and creates a tree with k clusters. So you've essentially got a bunch of trees that are clustered together, in k different clusters. And then what it does is at each level of each tree, it applies k-means again. So it reclusters and then reclusters and reclusters iteratively till it kind of narrows down to only the points it thinks matches by following the centroids of each cluster at each level. It's, that's kind of a lot of words, right? But you just have to think about it like, if I have my KD tree, I have a binary tree split based on a dimension. If I have a k-means split, then I'm not working with a dimension, I'm working with the features, and I'm clustering the full feature vector, and I'm clustering the ones that are similar in certain dimensions together. And then within each cluster, within each tree, I just keep doing that until I sort of reach a bottom layer of cluster. And then, I am following kind of the centroid of the largest cluster at each step. It's good for large data sets or higher dimensional problems, though not as good as hashing. It's kind of like a version of the KD tree that you can use on a really big data set, because it's not doing a binary tree split for everything. It is clustering things worse and then doing a split based off of clusters kind of recursively. So the last one, locally sensitive hashing, it works kind of like the hierarchical k-means, only what it does is creates hashes of feature vectors. So like a bucket of feature vectors, and then it just sort of vomits a bunch of feature vectors into each hash or each bucket, and then goes through the search space, the k-means phase, within each sort of bucket of data. And this is the one you usually use for higher dimensional problems, is hashing, because it is not as fast for a large data set as just a k-means, but it is more accurate if the data within that set is of higher dimensions. Because again, if I hash things, I'm not having to look at every dimension like I am with a tree or a k-means. I'm just looking at similar features within each hashed sort of group of feature vectors. So if I have a lot of dimensions like a SIFT output where a feature vector is 1,000 some entries, hashing is going to work a lot better because it can find dimensions that matter through kind of this buckets of features, versus kind of looking at all the features to see what matters through these recursive searches. So once we do our nearest neighbor search, if we come back, the next thing is we want to do our ransack, so a random sample consensus to remove outliers. So what random sample consensus is, this is a outlier detection method. So at this stage of FLAN, at this stage of feature matching, I can kind of use any outlier detection and filter, because it's, once you've extracted it this far into a feature space and done a nearest neighbor search, as far as the computer is concerned, as far as sort of the data structure is concerned, it's not an image anymore. It's just a vector with a bunch of dimensions. So you can remove outliers any way you feel like it, really. It just, because of OpenCV and the way computer vision works with image stitching, ransack is the best way to do it. And it's also worth noting that this algorithm is a generic outlier detection. So you can use this algorithm for pretty much anything. And it's used a lot in reinforcement learning, and it's used a lot in validating a model. And the way it works is it just grabs a bunch of random features that have been matched to sort of my source image, where I think I might have a feature vector that matches in the image to what I want to look for. So out of all these matches that I think are good matches, I grab a bunch of random features and fit a model to it. So this, it's the common way to think about it. The easiest way to think about it is like if you fit a regression model, you get a curve, right? And then you test other points in your data to see if they fall somewhere along that curve. That's kind of, the 2D version where you just have some equation for a line and you want to create that line with a random sample of your data, and then you want to test the rest of your data to see if it falls on that line. So it is, like I said, it's a really common technique, especially in generative adversarial networks, in addition to reinforcement learning. But it's essentially just grab a bunch of stuff that you've matched, make a model that tells me how all of it matched, and then test everything else against that model to see if it's in agreement. It can fail easily because it depends on the random sample you take, and if your random sample is a good representation of the model, because you have no guarantee that is the case. And the issue becomes, the larger your random sample becomes, the more confident in your model you can be, but the less features you will have to test against that model. So you have to balance picking enough random features to create a good enough model to weed out outliers, and leaving enough features out of the model to have a meaningful validation set of data. And then after we do ransack, we have our image stitching, which has a whole bunch of linear algebra and stuff in it that I'm not going to really go over because I promised you at the start of the semester. But essentially what we're doing with image stitching is we want to put all the images back together, and then we want to take the thing we found that we care about and mark it in the image, basically put it back where we found it. And the reason we use ransack for Flan is because it will give us a homography, which is essentially a measure of how similar the image with the features in it is to the initial image with no features matched. So it's taking our image with our features labeled and then mushing it back onto our image without the features labeled. And it does this by creating a coordinate transform like we've been doing since day one. And it essentially, there's the feature space or the image with everything in it. And then there's the initial image space where everything kind of is in our first image. And so we just transform our marked image of features into the same space as the original image and then slap them together. So it's, like we've been doing, like I said, one more coordinate transform at the very end to go from an image with all the features labeled and all the key points in it to our original image, and then we kind of line everything up. And there we are. We have run our feature matching algorithm with Flan, and weeded out any outliers and stitched the image back together. And we have completed the full computer vision object detection and classification lifecycle. And, like I said, we'll cover YOLO because it's sort of the next best layer up. But as far as an intro to computer vision goes, we've hit the goal where we've gone all the way from, what is a pixel to coordinate spaces to feature spaces to SIFT and SURF and now Flan and image stitching. So we've kind of, like I said, reached the point where we have filtered, we've detected, we've labeled, we've transformed. We've done all of our stuff to get to our final computer vision algorithm that will find things I want to find in an image. And so I mentioned this last class, but we can do all of this from scratch. We can kind of, we wrote a SIFT detector from scratch, so we can use that. We can write our own nearest neighbor search, which you guys have probably done more than once as computer science majors. We can write our own outlier detector or our own version of ransack, and we can do our own image stitching or homography with the images. Or we could not do all of those things from scratch because that would suck. And so I have a notebook that kind of covers all of this stuff through Flan I'm going to work through. But for next time, just a little preview of this idea of YOLO, or you only look once. This is where machine learning shows up at the party. And it works as sort of a unified model wherein it finds the features, figures out what they are, sort of extracts them, and then matches them all at the same time. So we're not doing, SIFT or SURF and then neighbor search and then ransack. We're doing everything all at once with a machine learning model. And I've got kind of some of the recommended reading up here. But what I'm going to do now is one. Okay. It is recording. I just wanted to make sure it was recording. Or else, no, whatever. Because I'm not doing it twice. Sorry. Okay. So here's our notebook from last time we ran through, and we started with, we're going to just use SIFT to do a brute force matching, and we get our stop sign and we got our time to see how long it took. And as you can see, it only found a few key points on the stop sign. Didn't go great. Now we're going to try it again using flan. So you can see here in the code, this is the part where we do our flan feature matching. This is the part where we've used SIFT first. So we've used SIFT to find our key points. And now we're putting those key points into our flan detector. And it runs, and you can see, we talked about this last time, you just have your loads test. It's a simple thresholding, and you can see with flan, it detected some more stop sign stuff, which is good, but you can also see this just vast ocean of flagged key points on the ground that we're not really getting here. So we just kind of took everything out of the box and ran it, and it didn't work well. So what we did next is we wanted to look at a more complicated brute force match. So again, we're just doing SIFT and a brute force matcher, and we're trying to find this stop sign in this image, and it didn't, even though it is clearly there. If we try this again using flan, you can see it kind of detected it, but just like last time with the flan detector, again, we have just a huge amount of garbage points. So the new code, we walked through that stuff last time. So we're going to look at now is we're going to, kind of see if we can do a better job by knowing kind of the bits and pieces inside of these algorithms. So the first thing we've done is for our SIFT detection, before we enter our nearest neighbor search, we're going to adjust our own features. So our options for SIFT with OpenCV is we can define the size of our feature vector, and the bigger the feature vector gets, the more key points we're going to find. We have our contrast threshold, which is our contextual anomaly detection bit, where it's looking at our key point, and it's looking at the background around that key point, deciding if it is different enough. So if it's that amount of different, then I'll label it as a key point. So the lower you make that value, the more features you're going to find, because we're essentially saying they don't have to be as different from the background to count. Our edge threshold, this is when Surf is doing its edge detection bit that we saw and wrote up our own version of when we made our own SIFT detector. So we're just telling it how many pixels makes an edge. And then the sigma, that's the standard deviation of the Gaussian blur. So again, when we did this on our own over the course of the semester, we created our own Gaussian blur that we then did before we did our SIFT feature detection. So it's just a measure of how much blurring we want to do before we go look for those features. So for our application now, where I've loaded in some SpongeBob images we'll look at in a minute, saying in our image, when it comes up, there's only about 10 bubbles in the target image. We're only looking for about 10 features, so we don't need a huge feature vector. And when we see the image, these bubbles we're looking for are pretty stark against the background. So we can bump our contrast threshold way up, which will kick out a lot of false detections. There's not a ton of background features in this image, so we don't need to worry about our edge threshold because we're not worried about finding a lot of edges. And again, because the features we're looking for are pretty obvious, we don't need to do a lot of blurring with our Gaussian blur step of SIFT. And so if we do this and do a brute force matching, we get our target image. So here's SpongeBob and the bubbles, and we're trying to detect these bubbles in this image. So our source feature is we've got this bubble that we're going to find feature vector for, and then we're going to compare that feature vector to everything in the image. And if we use SIFT with brute force, you can see we actually get a very good result. Almost all of the key points fall on the objects we're looking for. What you can see, and we'll see way more of in a minute, this area, this little white spot at the bottom of the bubble, is contributing a lot to the feature vector. And because it is such a big contribution to the feature vector of the bubble, most of the false alarms we have, like right here on the shirt and right here on the eye, are white. So it's choosing things that are a bunch of white pixels together as a feature match because its source feature vector has a lot of white pixels. And you can see again on the eye, it picks this up because of the curve of it. So when it is doing its source feature vector, it says I've got a lot of white pixels and I've got a lot of curves. And so it sees those in the eyeball and flags those. But otherwise, it does quite well. We've missed a couple bubbles. What we want to do is see how this does with the flame detector. So everything's the same through here. We're using our same SIFT. What we're then doing is kicking it over to Flan to do my nearest neighbor search. And as I do my nearest neighbor search, I want to pick out all of the matches that passed that neighbor search, put them into the good map matches, and then from here down, we're doing ransack and image stitching. So this is like the homeography for ransack happening here that we're not going to go through. You have an algorithm for it, but essentially you just need to know I've got my original image, I've got my image with my features in it. I'm going to filter out my outliers and then stitch the images back together. So if I do this with my Flan detector, so there's my source feature, and it's not as good. And the way we can see why it's not as good, we can compare my Flan detection, my nearest neighbor search, really, 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 really cared about that little white part at the bottom of the bubble. And so everywhere you see a lot of white with an edge near it, like the eyeballs, the shirt, the coral, it is flagging all of those because the way I have set it up as my default detector that OpenCV gave me, my source feature vector for the bubble is mostly just based off of that big stretch of white pixels. So if we want to do this better, what we're going to do is change our algorithm for our nearest neighbor search. If we come back up here and we look where we've declared Flan, we've got just our lows test before. Let's see, we've cut that out. Let me see where it's saying. Give me 1 second. Yeah, so here is where we are using a different FLAN algorithm. So the first one we used that gave us this terrible result is if we give FLAN either no algorithm or an algorithm one flag, which is just a very, very, very simple KD tree. If I want to do this better, then what I'm going to do is use for this guy, my algorithm 2, I'm going to look at it using hashing. And for my algorithm 3, I'm going to look at it using my recursive k-means or my hierarchical k-means instead of just my binary k-means. So I've got my matches for both of these, one for hashing, one for recursive k-means. I find my matches and I want to look at them. So these images are a little hard, but what you can see, I can go ahead and zoom in here a little to help out. So both of these worked way, way better. The hash search wasn't really any better than what I'd already gotten with SIFT. But my recursive k-means search, you can see I've got all these points on this bubble, and it's finding these other ones kind of out here in the far distance. And you'll notice in every case, it has not and is not going to detect the bubble SpongeBob is blowing because there is no highlight on the bottom. You know, even with my expanded composite and hierarchical k-means, it still cares a lot about that white highlight at the bottom. But by changing from just my stupid binary tree to something a little smarter, it's doing a much better job finding the bubbles it does find. And so this is just through our search. What we want to do now is we've got these two images that look way better. Let's see what happens if we add our next step and put in our ransack algorithm, and now suddenly it looks worse. Right now, the majority of points in both cases are almost all just SpongeBob. And again, you can see in both cases in that source image in the upper right corner, all it really cares about is that bottom highlight. And so all that kind of builds up to show that ransack is touchy. It has its own parameters that I didn't talk about too much in here, at least not in this notebook. I may add some for when we go over YOLO. But this really just shows that we do SIFT and we get some key points, and then we do FLAN to do our nearest neighbor search to get better key points that only match our initial feature vector for the bubble. And when I do that, I come up with pretty good results. You can see they're really only in this one image, there's an outlier down here kind of on SpongeBob, and the composite search finds like his hand here, but otherwise it's great. So when I put another filter on top of that to look for everything that matches my feature vector, it goes back into the list of key points and decides that no, the inliers I care about are at a inlier score that has to be so strong that only the matches I'm super confident in get pushed through. And because of the way I have run things up until now, it's super confident about white highlights. And then if we want to use our composite search and our k-means search and stitch this back together and kind of put everything where we found it, now you can see we've got all of our key points we wound up pulling out at the end sort of highlighted in these red X's. And from here, right, here's our key points on the image. This is kind of where the computer vision ends and the whatever you're trying to do with computer vision starts, because I've asked it to find features, tell me where those features are, and filter out anything that isn't that feature. And so now I've got a list of features, I've got their coordinates inside the image, and at that point, it's kind of on the engineer to do what the end goal is, right? Because if we think about applied computer vision and we think about everything we've learned until now, it's all been about getting to this point. You know, we've kind of done our computer vision point where we have fixed up the image, we have asked our SIF, SURF, FLAN, neighbor search, what have you, to go find features. And now I've got my features back. So, right, if I'm doing like an autonomous driving task, then I now have to train some model to understand, you know, this feature in this location is a person on a sidewalk or a car. Or if I'm doing facial recognition, you know, it's my job to have some sort of model that says, you know, these features found in this area with these dimensions and blah, 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 match like an angry eyeball, right? We've sort of done our job at this point of processing the image and finding the things that matter. And then it's kind of up to the user to then go in and do engineering with the features we found. So, all right, going to stop sharing. And like I said, I'm going to post project 3 today. It will be due on the 17th. And next class, we will be discussing YOLO. And then we'll start talking about some of the applications people may want to know more about. So anyway, yeah, thanks for listening, I suppose. I appreciate all of you. And we'll talk again on Thursday.